How you doing? It's Paul Seaver from Palm Beach Springs Water Company. This is an informational video about sodium organochlorine. What is it? What makes it different than hyperchlorite or hypochlorous acid? And the reason I say that is because we're talking about the neutral range of chlorine from basically 5.5 pH to 10.5 pH. At 5.5 pH, your hyperchlorous acid, everybody since COVID has been familiar with that term, I'm sure. And anybody who has a swimming pool knows exactly what hyperchlorite is, and that's at 10.5 pH. So that's the neutral range of chlorine, which is represented by this. So at 4 pH, you're 100% hypochlorous acid, and you're 0% hypochlorite. And then the opposite. And then, this doesn't stand for hypochlorous acid, but it does stand for hypochlorite. As you come down in hyperchlorite, once you get past here, you're all converted to hypochlorous acid. So that's where you're releasing your free chlorine in your swimming pool. So hyperchlorite's very complicated. It can convert to hypochlorous acid. Hypochlorous acid, however, cannot convert to hypochlorite. It's the other way around. So if that explains that. So your hyperchlorite is very corrosive. It works by dissolving organics. Your hyperchlorous acid is very oxidizing. It works by my terminology, burning up membranes, burning up organics. So both of them are considered pesticides by the EPA because they're dangerous to organics. One burns them up, one dissolves them. Very simple to understand. Okay. We're going to leave that alone. What we're going to talk about is acidulous. Acidulous, also known as chlorOrgano, also known as pH3 ocean mist. So acidulous basically means dissolved salts, the neutrality of dissolved salts in water. Something close to that. That's what acidulous means. Acidulous is made through a very special technology called high amp dual polarity electrochemistry ionics. And we'll get more into that. So that makes acidulous. Now, the unit itself is called chlorOrgano. And the product, the finished product that is made, is called pH3 ocean mist. So when we talk about acidulous, chlorOrgano, and pH3 ocean mist, we're simply talking about the same thing, other than we're talking about technology, equipment, finished product. Okay. So it falls into the neutral range here. So a little bit more of an explanation. So the EPA has defined properties of what hyperchlorous acid and what hyperchlorite is. Hyperchlorous acid, as defined by the EPA in the pH range, must be between 5.5 and 6.5. If the pH is higher than 6.5, as far as the EPA is concerned, it doesn't have enough strength, enough oxidation strength, because the ORP goes down as the pH goes up, of course. It doesn't have enough oxidation strength to burn through the membrane and deliver the chlorine, even if you can measure the chlorine present. So it's all by pH with hyperchlorous acid. It's strongest at 5.0. It's depleted at 6.5. Now, that's not Paul, that's the rule. Okay, I don't make the rules. Hyperchlorite must be stored at 10.5. If they were to go into a storage of a hyperchlorite container and find it at less than 10.5, it would be considered already disassociated. It would be already in action. It would be depleting itself. It's no longer stable, stored 10.5 hyperchlorite. Now, Generally, hyperchlorite stores for about 2 years. Hypochlorous acid, you would be lucky to measure any chlorine at the end of 3 months. And hypochlorous acid you have to use, in most cases, between 100 and 200 parts per million. So they have to store it much greater, then you have to dilute it, which really turns the clock on. So it's really a crazy kind of solution to work with. We don't do hypochlorous acid. You know, we have very sophisticated, top of the line, the most powerful generators that you can get by today's standards, and we don't have to mess around with hypochlorous acid. We have some much better solutions to use, and we don't mess around with hyperchloride either. You know, we don't have to mess around with any chemicals. We're the alternative to chemicals. So, as the alternative to chemicals, as a manufacturer of products, besides a supplier of equipment, I'm going to actually get rid of all my products so that I can take the chains off of what I can and cannot say. So because I make products and I make non-pesticide products, I'm only allowed to talk about non-pesticide actions. My equipment is very sophisticated, and I can build equipment, or I can have equipment built. I'm part of a team. I don't actually do the building. I'm the one that just turns in the order sheet. I'm the one that figures out what you need. Anyway, we can build equipment to do whatever you need to do, but I just have to be very careful because of the products that I sell, because they'll consider it to be misleading as a non-pesticide company. You can't talk about pesticide actions. Okay, that's the rules. I don't make the rules. I just have to live by them if I still want to be free and live in my country home in Arcadia and not a jail cell. All right. So, in the neutral range, why we're not so we're out of the ranges that the EPA recognizes as pesticides, as dangerous. That's what it means. Not necessarily effective. It has to do with dangerous. A lot of people get that confused, because once you get your EPA registration, your marketing company turns, you know, your risk and hazards into efficiency. So it's a little bit different. You know, now it's no longer a risk, it's an efficiency. We're effective at killing this at this concentration. You know, and then you read on in, and then it shows you how dangerous it can become. So anyway, that's a subject for a different day. If we're non-corrosive and we're non-oxidizing and we're in a neutral range where the EPA doesn't recognize it as being dangerous, how do we deliver our chlorine? That's a real, because it's not the chlorine that's the pesticide, you have to understand. One thing that people don't know, there's thousands of chlorine species, not just 3. There isn't just chlorine bleach, hyperchlorite, hyperchlorous acid, hydrogen peroxide, hydrochloric acid. 5, I guess. There's more than 5 chlorines. There's thousands of chlorines. But can you use those chlorines? Can you reproduce those chlorines in the same way that Mother Nature's making them? Can you reproduce it? That's what we do. So we're not considered an organic chlorine because we're made in a machine, but we are a organochlorine. We mimic an organic chlorine. We only use sodium chloride, period. No pH reducers, no additional salts, no additional contents of any kind. Sodium chloride only. So that's what keeps us safe. We stay in the neutral range. Why? Human body 7.4 pH. So the closer you can match the human pH with something that's effective to do what you're looking for it to do, that means you're completely safe for the human body. Okay, now our salts are not that great. All right, usually in chemical solutions, you'll be 26% or more salts, and in a combination. So that's what makes them dangerous. We're at 2% or less salts, single salt. No danger whatsoever. We have less salt in our solution than you put on your hamburger. So it's impossible for it to be dangerous. You have to have, few people know this or ever heard this before. Everybody thinks that there's 3 essential ingredients to life. You gotta have air, you gotta have water, and you gotta have food. You're absolutely correct. Few people ever heard that you have to have sodium chloride. You don't have any choice. It's essential to life. If you have a diet that completely is sodium chloride eliminated, you will die. You don't have any way to regulate your body. It regulates everything in your body. And let's get rid of one other thing too that people talk about. Hypochlorous acid is not created in the human body. This term, hypochlorous acid, that I cannot use because I'm a non-pesticide company, is a term that is very loosely used. When you are a manufacturer of products such as hypochlorous acid, and you tell somebody that it's the same as the hypochlorous acid that is produced in your body, you are not telling them the truth. The hypochlorous acid that you produce as a registered pesticide, defined by the EPA, has a pH of 5.0 to 6.5, and your ORP is 900, 950, whatever, but it's over 800. You guys know at 800 you're dead. So you're trying to stay at 950 or higher. And your available free chlorine, is much higher than, and you couldn't read the available free chlorine in blood. It's most certainly not going to be 200 part per million and above. So if you had 200 part per million available free chlorine as hypochlorous acid at 5.0 to 6.5 pH and an ORP of typically 950 in your body, you would be in the hospital. You wouldn't even be in the hospital. You would be in the morgue. You would be dead. Dead. Don't listen to that marketing crap. They're just making a play on the conversion of sodium chloride in the human body and the slight properties that are made to maintain separate specific functions in your body. And yeah, they consider it to be free chlorine produced as hypochlorous acid. Your body is a dual polarity organic electrochemistry generator. It has the ability to take that salt, neutralize it, convert it, and do what it needs to do in your body with it. So they're not telling you the truth in the context of that's not what they produce. The water that you drink is more closer to what that is than the solutions that they produce. That's for sure. All right, so we'll get past that now. Get back on track. Okay, so we got an organochlorine in a neutral range that's non-oxidizing, non-corrosive, non-regulated, and not recognized as a pesticide. And for what its purposes, it still works pretty good. I shouldn't say pretty good, it works real gosh darn good. So how can it be? I'm trying to be very selective what I say, because I don't want anybody to come back on me from the state or the EPA or anybody else and say, oh, well, now look what you're saying. So this is very complicated to try to explain. So let's just talk about ionic product. Like I said, it's not the chlorine that's the pesticide. It's the pH range and the ORP and the corrosiveness and the oxidizing properties of the mediums. That's what makes them pesticides, not the chlorine. We got chlorine in our bodies. There's chlorine in the air. There's chlorine in the ocean. There's chlorine in the lakes. Anywhere organic living beings are, there's chlorine that's being emitted. They say that's what the smell of the ocean is. The smell of the ocean is just a combination of thousands of different organic chlorines being released at the same time, and that's the fresh scent of the ocean. Go figure, why does a pool smell fresh? Same thing. chlorine. So anyway, so we have to talk about ionic product. What is ionic product? It's not something I created because I didn't create this chart, okay? Ionic product. There's two different types of electrochemistry generators when we're talking about chambers. You have one flow in, two flows out. One side will be high, one side will be low. This is the high side, alkaline, acidic water, low. Now, in single polarity nano generators, they're only working on one side or the other. So either you're getting hypochlorous acid or you're getting ionized water. You know that people drink alkaline ionized water. So that's what this sort of a configuration will give you. That's all it will give you. We're not talking about this kind of a configuration. We're talking about this kind of configuration. This is a custom configuration that nobody else has. So it's one in and one out. Everything's done within the chamber. Okay? So now the difference is, we also have chambers like this, but our chambers are perfect. We got power on both sides. So when we use our chamber like this and we power both sides, we isolate perfectly the acidic from the alkaline. In a nano chamber, you don't. You'll still have some crossover, so you won't get a perfect split. Okay. So in our chambers, you get an absolute perfect split. We won't get into it. We can prove it. It's no big deal. This is all mathematics, and I got visualizations to prove it too. So once you get these perfectly split, you can put the same charge on either side, on all the ions, and you can create your ionic product. When you do it this way, what you're doing with a single flow in, single flow out is, I use two of my grapes. Everybody knows water's made of two ions, a basic and an acidic. But what you do is you bond them together. Okay, with dual polarity, you bond them together for one. Okay, so now you got a single ion that was created by two ions, and depending on how much charge you put on them. Okay, I got machines that go up to 30 amps here. You know, so we can put 30,000 times the charge on these than they had. So we can not only bond them together, but we can compress them into the same size a single one was. One of these days I'll get somebody to run the mathematical equations on that. But there's a reason that we know that we can do this. We don't need the mathematics. Here's why. Most of my understanding from this come from agriculture, having to work with foliar treatments. How do you get a foliar treatment to absorb past the membrane of a leaf, become flow mobile, and translocate through the entire structure all the way down to the tips of the hairs of the roots, the entire structure, for 100% efficiency? You have to be able to get past the membrane. You have to be able to become part of the system. And so that becomes very difficult. So in most cases, they're using oxidation, right? They're using acidics to burn into the plant and burn the plant up, do enough damage to the outside of the plant, and the rest of the structure will die. You know, and they do that with stuff like glyphosate and things like that. Well, you don't have to do it that way. You can do it the way glyphosate was engineered. We're not going to get into that. That's a whole different subject. Wait, here's the thing. Almost everything you do, including the water that you're using itself, is clustered. You have clusters. You have clusters of molecules. They're all bunched up together. How do you expect them to pass by something? They can't. Or sit on the outside. That's why they use oxidation and corrosion to blow it open, right? Blow it open. Let the chlorine in. But what if you can break up that cluster into a single molecule, single ion that carries the chlorine within the molecule, held in there by the power of the ion, and it just slips right by the membrane. Guess it won't be eating that great. I gotta get it before the doggies do. I don't think they're good for dogs. Welcome to ionic product. That's what ionic product is. It's the ability to completely manipulate everything within the aqueous medium using high amp dual polarity. Unless you use high amp dual polarity, you can't do that. It's impossible because you don't have a single polarity medium. You always have a dual polarity medium. That's why it's clustered and it doesn't have any energy. So you got to pump that energy in there, and you have to decide, do you want it to be basic, do you want it to be neutral, or do you want it to be acidic, okay? And you could think about this and you could relate this really closely to statics. It's just like static electricity. So water is a weak conductor of electricity. It doesn't want to pass through, so the electricity, the protons or the electrons, they get trapped in there. And then once they become overloaded, then they have to release and they have to go somewhere. And water always wants to go to neutral because Mother Nature always wants to neutralize everything. Mother Nature always wants to create that neutron. And we're helping Mother Nature. And we're doing it instantaneously with an extra high charge in both polarities and slamming those suckers together. Slamming them together with 10,000 plus the power that Mother Nature uses. So we're doing it instantaneously. And once they're all slammed together, they're all single ion, single molecules of water now. Forget whatever they're holding. But they're single ion, single molecules of water. Now they can't collect together anymore. They can't become a bunch. They can't become a cluster. They have so much power that they push each other away. Think about two same polarity magnets, if you will. You can't push them together. No matter what you do, they are not going to stay together. They're going to push each other apart. Stored charge. So like stored charge cannot cluster. It only repels. That's ionic product. I got this online. I didn't create it. This is the measurement of ionic product. The measurement of ionic, so in electrochemistry, the measurement of ionic product is a mathematical equation. It's not a meter. So you have to be able to do the mathematical equation. This is where those guys with the PhDs and stuff come in, and where the rest of us are gone. We just have to accept their knowledge as being true and factual. I can't do the equation. Hell, I don't even know what the damn equation means. I know a little bit, but not enough to even fake my way through a conversation. That's complicated stuff. I don't know mathematics that deep. Anyway, here's a chart. This is a chart of the increase in ionic product having to do with heat. And so the cross-reference with the mathematical equation at 10 amps is the equal to the same amount of ionic product in 200-degree boiling water, but with no heat. So the way the water gets molecules excited and does this thing is through heat. And so we're doing it through electricity. So we're exciting those molecules, but we're not really exciting the molecules. We're exciting the ions, and so is the heat. The heat's not exciting the water. It's exciting the molecules in it. That's why zero water is less efficient at heating things. Anyway, at carrying heat, or either gaining or removing. We won't get into that. So the single molecule has as much charge on it as you could put on it, period. If it could put any more on it, the machine will put it on it. So it puts the maximum that it will hold. The machine is more powerful than the ion, so it can put as much on there as it needs to put on. The only time we put more power into the machine is if we want higher flow, so it can do it faster, it can keep up with it faster, because it doesn't have as much time to do it. So you got to hit it hard and quick. It just makes sense. So the faster the flow on the machine, the more power you got to add to the solution. The slower the flow, you know, you can knock it down to 10 amps. You know what I mean? Yeah, you kick up that flow, kick it up to 30 amps. You're still doing the same thing. You're just doing it a lot faster. All right, anyway. So now you got the power of these ions are pushing each other at the same time. So not only we're talking about the difference in driving past a cellular wall through an aquaporin. So in order to drive past an aquaporin, you have to be down to single molecule, single ion. You have to have an octagonal constant of -1 to 1. And that's the only way you can pass through an aquaporin of a membrane without damaging it. And that is our description. And it's like phew, for most everybody. So that's why what I'm saying is you got an aquaporin. Okay, this is how your water travels in your body. You have to get a molecule small enough by itself to be able to fit through it. That's what that means. Otherwise, you have to blow it open to get to the inside, drop your chlorine, do the damage, get out of town. But now you destroyed that cell. You didn't sterilize or clean or sanitize or bioselectively kill the bad bacteria or whatever it is that you're going after. I'm trying to talk in general so I don't get myself in trouble here. You destroyed the whole cell. That's oxidation and corrosion. Ionic product is keeping the cell intact, doing the job that you need to do inside the cell without damaging the cell. That's why it's not a pesticide. That's it. That's it. That's why in restaurants, when they use it, it heals their hands. Makes their hands good because it's healing the cells. And so you generally the ORP is less than 600. It just all depends on how concentrated it is. Now, perfectly food safe. Spray it right on food. These grapes that I'm eating right now, I washed them with Acidulous this morning. So I've had these grapes. I bought a big old bag of them. You can only eat so many, you know. I've had them for a couple weeks. Or if you notice, they're still like new. Okay? Hydrogen water. Ocean mist. I opened the container this morning and I saw 2 grapes, had a little bit of fuzzy mold on them. Plucked those 2 grapes out, grabbed my ocean mist, rinsed them all down, and grabbed my Aspirate, rinsed them off, like brand new. Can't even tell. Can't even tell. You think you just got them. Squeaky clean. I don't know if you could hear it. Squeaky clean. Still crunches. And I revitalized them twice with Aspirate. So, food costs too much today. I can't throw them in the garbage. So organochlorine is just, it's 100% safe. We're only using sodium chloride as an electrolyte. So a lot of people don't understand that word electrolyte. Electrolyte is just salt. That's it. That's where you get your power from. But a typical salt ion carries less than 1 MA of electrical charge. Depending on what side of that salt you have is depending on what charge that you're getting, you know. And, you know, if you do this in a highly concentrated way where you're transferring power that way, that's called mass transfer. So we don't do mass transfer. What we do is advanced energy transfer, because we don't need a massive amount of material in order to do the job. We need a minimal amount of material. I don't know if I already said it, but most of your chemicals are 26% salts and above. We're at 2%. Because we're increasing the potential of the salt, the single salt, with electricity. And with the chemicals, they're increasing the potential of the salt with other salts. They're getting a reaction between them, so they need much more salt. So the salt that's in our solution is less than what you put on a hamburger. And you have to have salt in your diet. You have to. It's essential to life. So there's no way it can be harmful to you. So in all of that, that's why we are not a pesticide. That's why we are non-regulated. That's why you can use us any way you want, anyhow you want, and it's perfectly safe, and it's still going to do what you need it to do. That's it. And for me, I'm a certified FDA PCQI, so I know what I'm talking about. I have to work in food service. I work with restaurants. I work with dog kennels. I work with all sorts of different things. So these people will tell you. You know, you go on my reviews and look at the people who work in these industries, and they're going to say it's the most fantastic product that they ever used. They could tell you whatever they want to. I can't tell you a gosh darn thing. But, you know, it is what it is. And, so ionic product and the ability to fit through an aquaporin of a membrane gives you an idea of how small of a particle size we're talking. So we said something before about the fact that, you know, stuff like hypochlorous acid is clusters, okay? Clusters. So they can't fit into porous material. And look it up. It's only considered a surface sanitizer for that reason. That's it. You have to clean the organics first, then you can lay it down as a surface sanitizer. You can't expect it to clean out porous materials. That's why they want you to lay down a thick layer, hoping that you're going to smother what's ever in the pores. And it never works, of course. Otherwise, they wouldn't have the problems that they have. So, with COVID, everybody talked about how COVID could lay on countertops. It could be on this, it could be on that. And so, you can't predict the size of COVID. The only thing that you can do is go to the recognized information about what is the smallest particle size of a COVID particle. Because at that point it's a particle. So the smallest particle sizing of something like that is 0.004 microns. Our average micron sizing is 0.0001 micron. So we are much smaller than a particle size of a COVID spore. That's what I was trying to kick out before, and I couldn't kick it out of my mouth. Spore. A COVID spore. Okay, so a COVID spore cannot hide within a porous material deep enough that we can't get to it. And that was the problem with clustered solutions. They can't get into porous material. COVID spores are as small as 0.004 microns, which is extremely small. And that's that. But it can't hide from us. And then we have other ways that you can use ocean mist and ultrasonic humidifiers and other things like that. We're talking about Acidulous as distribution methods because it's single ion, because it's neutral and it's single molecule. You can suspend it in the air as an aerosol. It's very unique. You've heard people talk about doing that with hypochlorous acid. I'm not going to get into the entire subject. I could do a whole video on why you don't do that with hypochlorous acid, number one, and number two, you're wasting your time doing that with hypochlorous acid because it's ineffective as soon as they put it in the air. Immediately gone. Boom. You have to understand what hypochlorous acid is. And you have to understand that, I'm glad I just mentioned that because I skipped an entire subject. What chlorine is acidulous? It's not hypochlorous acid. It's not hyperchlorite. What is it closer to? What does it most closely resemble as an alternative to? Both. Both. Because we're so stable that we can produce it at whatever pH we need to. Now, we purposely do not go below 7.4 pH. Number one, we don't have to. Number two, we'd be considered hypochlorous acid, so we don't. Secondly, we do not go above even 9 into 10 pH. The strongest I've ever made it is at 9.8. That was 2,000 part per million concentrate. That's some strong stuff. All right? But it's still not considered hyperchlorite because it's not at 10.5 pH. So we stay between 7.4 and about 9.8 in my shop, because I keep myself out of trouble. So in that statement, what I'm going to say is this. If you wanted to label a comparison, the comparison would not be hypochlorous acid. The comparison would have to be hypochlorite, because we store chlorine. How do we store chlorine? It's because you have to understand how hypochlorite is made. Hypochlorite is made by storing chlorine gas to sodium hydroxide. But in the context of hypochlorite as an EPA registered pesticide, they're using a class 8 corrosive, and I don't know what chlorine gas, I don't know what its class is, but anyway, it's a class of its own, that's for sure. You're talking about dissolved chlorine gas, dangerous stuff, okay? But they're using commercial chlorine gas, and they're using commercial sodium hydroxide, and they're bonding them together for hyperchlorite, okay? So in our chambers, because we're high amp dual polarity, we are making our alternative to sodium hydroxide. Now, the EPA registered sodium hydroxide is a class 8 corrosive, extremely dangerous to all organics. Electrochemistry alternative to sodium hydroxide, as it's being produced, has an ORP of a negative 850. Nobody's going to say that's corrosive. That could neutralize just about anything. Just about anything. That will neutralize hydrochloric acid. It has enough electron donation to wipe out anything. A negative 850 ORP is an extreme amount of electrons. Electrons are what neutralize protons. Protons is where your acidics come from, is where your reactive oxygen comes from. So when you start knocking them out, you know, who's ever got more power? Who's putting more power in? Are you putting more positive charge in for your protons? Are you putting more negative charge in for your electrons? Now the key with Acidulous is it's balanced. It's perfectly balanced. One has no more power than the other. So that's why we can store, well, I shouldn't say that. It's balanced for making organochlorine. I don't know that it's 50-50, whatever the balance is that's required between AC and DC. So the more DC you pump into the environment, the more protons you're pumping into the environment. The more AC, the more electrons. So somewhere in there, there's a balance for what your finish is, you know. And so that's the way those units are programmed and set up. That's the simple version of it. They're very complicated. There's lots of membranes. Think of membranes. It's not a membrane like an RO membrane. It's an electronic membrane. They're flow through. You don't put no pressure on them. So they're flow through. And what you'll have is you'll have stacks of membranes. And so think of each membrane as a different stage in what you're trying to do. But they all have to work together. So it's very complicated. So in this context, what we are doing is we're producing our version, our alternative, sodium hydroxide. And so the reason it's the alternative, that has to do with the pH range. So you're in the pH range, you're in hydroxide. Okay, you're all basic at that point, 100% basic. And in the low range, you're in hydrochloric acid. You're 100% acidic down at the bottom end, 2.4 pH. So you got one extreme and you got the other extreme. So one's creating dissolved chlorine and the other one's creating sodium hydroxide at the same time, in the same environment, in the same chamber. And so, of course, they bond together, and the finished product is chlorOrgano ocean mist, Acidulous. But the difference is because we're applying so much power, we have total control over stability. So where hypochlorous acid, let's say, as for instance, is completely unstable, you're lucky if you could still read the chlorine after 3 months. And some people are going to argue that, but I tell you, I ain't seen a damn one that you could. So it's not even very good for very long. They'll say, oh, you could keep it in a jug for 3 months. Well, at that end of the 3 months, you can't use it. So that's an inaccurate statement. Okay, it's not strong enough to use. And you have to check the pH with hypochlorous acid. You cannot check it by available free chlorine. The reason is it's not the available free chlorine that does the job. It is the ORP. The available free chlorine in hypochlorous acid is powerless without ORP. It has to have a strong enough ORP to burn its way through the membrane wall, or the chlorine just going to sit there. That's why above 6.5 pH is considered ineffective. And of course, now on the opposite end, we got the hyperchlorite, which has to be stored at 10.5, or they already consider it to be releasing. It's already done. It's no longer stable. So in that one, they're kind of more looking at stability than anything else, right? Because the stability of it is the performance of the product. So now we can stabilize at any pH and at any available free concentration, because we don't rely on corrosion or oxidation. We only rely on the ionic product. And the ionic product has absolutely zero to do with ORP. We don't want a high ORP. We don't want to cause any damage to the cellular wall. The benefit, the value of Acidulous is the fact that it's non-regulated. Okay? I think I mentioned, I'm not sure, that I'm a certified FDA PCQI, and so I have to understand a lot of stuff that has to do with commercial food production. Doesn't mean I could write the safety plan for a manufacturing plant, but it does mean that I understand it. And it also means that I understand how to bring my products into a plant and show them how we can use it without having to reinvent the safety plan. And so the key to that is, the whole benefit to that is that we're non-regulated. As long as you're non-regulated, you can put yourself in any place you want. That as long as the operation believes that it's not going to hinder their operation in any way, shape, or form. I mean, so I don't want that to be taken out of context. The point of the matter is any place that you feel is appropriate to slip that in as an additional preventative control, you can, without reinventing the safety plan, because it's non-regulated. If it were regulated, then you would have to reinvent the entire safety plan. Anybody who does food service safety plans will agree with that. But since it's non-regulated, and we work with places, we're working with some places in Nebraska right now. Let me get a drink here. I'm losing my voice. And they got the FSIS guys and the USDA guys, and everybody's right there, and they all think it's absolutely fantastic. And you know, when at first when the guy went into the plant and they says, oh, no, we can't do anything like that, you know, because we've got a safety plan. And I already told them ahead of time what to say. I said, when they say safety plan, you just say right off the bat, you say non-regulated preventative control. I said, and then you're going to get their attention. And so that's all he said. He says, well, we can't do it. And he says, listen, I only got one thing to say to you, non-regulated preventative control. Oh, well, let me hear about it. That gets people's attention. You gotta have stuff that's non-regulated. You gotta have stuff that you can use. You gotta have stuff that isn't gonna hinder your program any further. And that's what this is all about. That's where its value is. I could very easily take a little hydrochloric acid, dump it in my product, turn it into hypochlorous acid, get on list N, the list of poisons, the big lie, get on list N and sell a gazillion gallons of this stuff everywhere. It's not my objective. I'm the chemical alternative. I want you to have safe products that you don't have to use as directed. List N is nothing but poisons. Better than nothing list. They got chlorine dioxide on it, for Christ's sake. Give me a break. But that doesn't tell you anything. Bad, bad, bad stuff, okay? The problem with List N, they were trying to do something good. Everybody had a problem getting solutions, this, that, and everything else, so they had to do something because people were panicking over nothing. They just clean their houses. You don't need to sanitize them. How do you sanitize a particle? Everybody in science knew what kind of BS all that was. You can't sanitize a particle because a particle's not alive. It needs a host. What are you gonna do? Sanitize all the hosts? You got to clean the particle. And then the stupid masks. You got particles as small as 0.004 microns. If you had a mask that was that tight, you wouldn't be able to breathe through it. So masks were a joke. So anyway, that's besides the point. That's a whole other subject. So anyway, you got to use good products. You got to get the chemicals out. You don't need them. And you can buy products, you can buy equipment, you can put this stuff into operation in your places. You're not held hostage to any suppliers when it comes to cleaning products. Remember, I can only use the word cleaning. You know, so a proper cleaning does not require sanitation. Look it up. Nowhere in the world does it say that they recommend sanitizing. You know what they recommend sanitizing? As a last resort. A last resort. They recommend cleaning first, sanitizing as a last resort. Nobody knows that. Look it up. It's real easy. Look it up. So anyway, I'm going to put an end to this video right here because it's already too long. So that's just some information on Acidulous organochlorine made through high amp dual polarity electrochemistry. And I have a few dealers. There's a few places to get it. I personally only make a little bit of product because that's not really what I do for a living. But we got Nate out in California, and there's Tim out in California, and there's Scott in Nebraska. There's James in Michigan, and down here in South Florida, there's quite a few people. There's Sal, there's Kevin, there's Nico, there's just quite a few people here because this is where I started at, so there's quite a few people here. So all these people, you know, I leave the product selling to them. I stay out of it, and I'm their backup. I'm the guy who comes up with the stuff for them. I'm the one who defines it for them and gives them their descriptions and tells them, you know, all the information that they need for their customers. I have a few customers of my own, but that's mostly for R&D. I get all my information from them, you know, and see if there's any problems or whatever, you know, and that way I could tweak stuff. I get my own information from my own working world. So anyway, I hope that helps people understand a little bit about advanced electrochemistry and the products that you can make from it. And like I said before, everything from 11.8 pH to 2.4 pH. And they're all alternatives to the other things. And so if you really need those commercial chemicals for what those commercial chemicals were originally created for, these alternatives will not work for you. Those are commercial chemicals that were designed to do some very tough things. We're talking about in your personal life or end users such as restaurants, stuff like that, not the heavy duty stuff. You're not gonna take my alternative to hydrochloric acid. You're not going to be able to etch concrete with it. That you're not going to be able to do. That's why I mean they're two different things. So we're talking about in the use of normal everyday human use for your own body, for food, for your animals, for the environment in which you live in, not commercial and industrial usages, just to make that point clear. Now, some of the chlorine products are, you know, we can make them super strong like that. And they're plenty strong for commercial, but that's a whole different deal. That's different equipment, commercial equipment. So anyway, that's it. That is my long, boring video on Acidulous. I hope you enjoy it.